In this section, we're going to look at the derivatives of a couple of different functions that we haven't actually covered yet. So at this point, we know how to find the derivatives of things that are being added or subtracted. We have the product rule to find derivatives of functions that are being multiplied together. We have the quotient rule to look at derivatives of functions that are being divided. We have the chain rule to help us find derivatives of composite functions. And in this section, we're going to discuss finding derivatives of exponential functions, and then there'll also be another video on logarithmic functions because exponentials and logarithms are related. So when you look at what your book says about derivatives of exponential functions, we have here, specifically, it's looking at e to the x because the natural base e gets used a lot in different business and economic applications. So derivatives of e to the x and e to the g of x. So e being raised to a function instead of just the variable x. And that second one, e to the g of x, that's really just a chain rule extension of the first rule, the derivative of e to the x. Both of these, I believe, are actually proven in your book. I'm going to go ahead and walk you through how they're used without proving them. But if you're interested, you can take a look at the proof in the book. So we have our definition that we just talked about. So it says definition, if y equals, if y equals e to the x, then y prime equals e to the x. When we're looking at the natural base exponential, so the kind of natural exponential function, it is its own derivative, and it's really fascinating. There aren't really functions that do that very often, and so that's what we see here, right? Y equals e to the x, and y prime equals e to the x. On the other hand, if y equals e to some function of x, then y prime equals g prime of x times e to the g of x. And again, that's just coming, since this is its own derivative, it hangs out in the derivative, but whatever this function was, it's going to have a derivative, and so the chain rule says that we need to multiply by whatever that derivative is. Okay, so that's what we've got in terms of definitions. Let's look at a couple of examples. So find, let's say, y prime, find y prime if y is equal to 3e to the 17x squared minus 4 plus 12, something like that. Okay? So, when we're dealing with a function like this, we can think of this as two separate functions, right? In the sense that if we want to take the derivative of multiple terms being added together, we take the derivative of each term separately, and then we can add the derivatives together. When we're looking at this first term, 3e to the 17x squared minus 4, it will be its own derivative because it has a natural base. It has base e. So 3e to the 17x squared minus 4. But because that exponent that we're raising the e to is itself a function, we need to use the chain rule and multiply by the derivative of that function. And the derivative of that function, 17x squared minus 4, we're going to have the 17 times, we're going to bring the power down, times the x. Technically, we would subtract 1 from the power, but 2 minus 1 is just 1, so that's just an x. The minus 4 will go away because the derivative of a constant is 0. Similarly, this plus 12, the second term in our function that we're looking at, it's also going to become 0 because the derivative of a constant is 0. And so then I'm just going to rearrange my terms here a little bit so it will look nicer. Let's see, I've got 17 times 2 times 3, right? 17 to 3. What on earth is that? 17 times 2 times 3. 17 times 2 is 34. 34 times 3. Hold on just a second. This is not the kind of math I do well in my head. Okay, so that's 102. And then we had this x. And then we have e to the 17x squared minus 4. And that is our derivative of that function.